To determine if a function is even, odd, or neither, we're looking at symmetries. So one way that we can do this is graphically. I don't really know why I felt like I needed to hide this graph, but anyway, here it is. This is the graph of this function. Now, even functions have y-axis symmetry. Odd functions have origin symmetry. And for our purposes, these things are really equivalent. If a function has y-axis symmetry, then it is even. If it's an even function, then it has y-axis symmetry. Similarly for odd, if a function has origin symmetry, then it's odd. If it's odd, then it has origin symmetry. So for our purposes, these things are, almost interchangeable terms. They're kind of talking about different things, but they go together. So if we can tell one, then we know the other. So my graph here, the axes aren't super clear, but here's the y-axis, just to make sure we can see it. And here's the x-axis. Okay, so if I'm looking to look at the graph and think through this idea, y-axis symmetry means that if I hold the y-axis still and flip that graph over or reflect it, that I should end up with the same picture. So again, if I hold the y-axis still and flip it over, I should end up with the same thing. Now, if we take that graph and reflect it over the y-axis or mirror it across the y-axis, what happens is that a point here is going to end up over here. This point here is going to end up sort of over there, right? Everything gets flipped in the x-coordinate. So what that would look like then is something, I'm not trying real hard to draw this perfectly, but something like that, which is not the same as the graph that we started with, which tells me that it's not even. Again, just because that's different. Now, origin symmetry, the idea is that the origin stays still and we flip the whole graph upside down. You can think about that as reflecting or as rotating, but basically like I'm putting a pin in at that pink point, the origin that I've marked, and flipping the graph upside down. I might be able to actually do that. No, okay. I'm not skilled enough to do that. Or Notability won't let me. I don't know. It doesn't matter. But if we rotate that upside down, then what's going to happen is this little bit of the graph that's sitting below the x-axis is going to be flipped to sit above, and vice versa. So we're going to end up with something that looks something like that. Again, if the thing has origin symmetry, if it's an odd function, I would need that to look exactly like the graph that we started with. Doesn't, so it's not odd either, which means this is neither. So we have our answer. For the sake of doing it, though, because this will come up as well, that we need to be able to kind of check this way and see what the algebra looks like. We're going to look at this analytically also. That just means, symbolically, like working out the algebra, basically. To do that, what I'm going to do is find f of negative x and simplify. So I'm going to take my function, and where I had, switch to a different color. Where I had an x before, I'm going to replace with negative x. What I'm doing, it's helpful here to think of the negatives as being like opposites in the number line sense, right? In the same sense that like 2 and -2 are opposites because they're the same direction or same distance from 0, but in opposite directions on the number line. That's what's happening. I'm replacing x with its opposite. So I'm just flipping the sign of the input, which is going to, send me from, being over here to being in the same position, but on the other side. That person got weird. I don't know. And then I'm going to simplify. -x times itself, the negatives cancel. I get x squared. 3 times negative x plus 3 times -x, so that's minus 3x minus 2. And then what I want to do is compare these two things. And the comparison I'm doing is to see if these are identical, which they're not. For a function to be even, we need f of -x to be exactly the same thing as f of x. Well, that doesn't happen here. So it's not even. For a function to be odd, we need f of -x to be exactly opposite f of x in terms of the sign. So I would need, like what happens here, I would need the signs to flip on sort of every term, or it to be like I just put a negative sign out in front of the function and distributed it through, right? So opposite in terms of the sign. Another way of saying that is that, reflecting this way is going to cause you to reflect this way. But that doesn't happen here either, right? These terms have the same sign. These are opposite in sign. These have the same, so it's sort of, all mixed up. That we don't get either the same thing or the opposite thing, so it's not odd either. Which again tells me that the function is neither even nor odd, which in turn means that it has no y-axis or origin symmetry, which are the symmetry types that we're looking at when we talk about even and odd functions. Okay, well, so there's an example of testing a function for its parity and symmetry. Please let me know if you have any questions.